Welcome to Intro2Astro 2024.
The other topic that I'm covering today is radial velocities. Radial velocities are one of the most common ways to detect exoplanets. And so I want to talk to you guys about how this method works and how we can find exoplanets. Once again, this will not get too much into the code behind it. The demo, which I've also provided here, will give you a more in-depth look into the actual process of how you turn data into actually getting masses of planets. But once again, I think understanding how it works is something you need to do before using it. So let's get started. So yeah, the radial velocity method of detecting exoplanets, also called the Doppler method, is the earliest method of detecting exoplanets. It's the very first one that we used to discover planets around a main sequence star. So have you guys heard of the Doppler effect?
Yeah, we talked about this briefly earlier in the workshop when we were talking about exoplanet detection methods.
Oh, perfect. In that case, yeah, very briefly, just in case there was anyone who missed that. The Doppler effect is what happens when something is emitting waves while heading towards or away from you. So you might be able to hear this when you hear like a fast car rush by you, and it makes like a wing sound, because the sound are the waves in air that are kind of getting compressed as the waves move, as the source of the waves moves towards you. But it also turns out that the exact same thing happens to light coming from stars. So as a planet orbits a star, it's going to move around a lot, but the star will wobble a little bit too. Like as a planet circles a star, it's going to trace out big paths around it because the star is exerting gravity on it. But the planet is going to exert gravity on the star too, and that's going to make it wobble around a little bit. And importantly, the heavier a planet is, the more gravity it's going to exert, the more it's going to make the star wobble. So if we had a way of seeing how much the star wobbled, we could figure out how heavy this planet is. And it turns out that there is a way to do that. So stars emit a lot of light. And it turns out that light undergoes the exact same Doppler effect that sound does. So as a planet circles a star, the star is going to trace out smaller circles from the gravity due to the planet. And the light is going to change frequency in the same way that sound changes frequency. But the frequency of sound, or the frequency of light, is just the light's color. And so as the star wobbles back and forth, the star's color is going to change, getting a little bit redder or a little bit bluer. And so luckily for us, there's a really easy way, well, comparatively easy way, to measure how much redder or bluer a star is getting. So when observing a star, we can measure its brightness as a function of wavelength, called its stellar spectrum or stellar spectra. Normally, we would expect the spectrum to look smooth, but when we look at it, we see really thin peaks and really thin valleys in that brightness curve. And those are due to the presence of atoms or molecules inside a star. Each atom or molecule has its own little wavelengths of light it absorbs really well if it's cold, or emits really well if it's hot. And so light of all wavelengths gets emitted by the star, but the atoms inside the star's outer layers interact with that light. If the atoms are colder in the inside of the star, they absorb their own special wavelengths of light, causing dips in the spectrum at different wavelengths. And these are really, really thin dips, importantly, like a fraction of a nanometer wavelength. And on the other hand, if those atoms are hot enough, they emit at those same wavelengths, causing peaks in the spectrum. So if we have really nice, easily identifiable, sharp lines in the spectra, we can see them move, shift to the left or right, to the red or blue, a lot more easily than we could see the entire spectrum shift to the left or right. So if we figure out how much they're shifting, we can figure out how much the star is moving, and then we can figure out how heavy the planet is. So let's see what that looks like. This is a sample graph of the radial velocity of a star over time. For most planets, a radial velocity curve will look really similar to a sinusoidal curve. A plot of the radial velocity over time, a radial velocity graph, is entirely described by just a few different parameters. So there are 5 parameters of a planet that can describe its radial velocity effect of the star. The period of the planet, the semi-amplitude of that signal, the time of transit, and then the eccentricity and the argument periapse. So let me get into what these are. The period P is probably the simplest. The period is the exact same as a period of a wave. It's the time it takes for a radial velocity cycle to take place, for a planet to make one orbit around the star and begin the same curve anew. So it's a different distance between peaks of that curve. The time of transit, T0, is the epoch. That tells us at what time does a planet transit. And that has the effect of shifting the radial velocity curve to the left or to the right. So normally at a time, at an epoch T0, when the planet is transiting, the star, the planet is just straight up pulling at a star. And so it's pulling at a star straight towards us. But if you look at the circle that the star traces out, the star is moving tangentially to us right at that time. And so the radial velocity curve is 0, but increasing. So like right here, we would expect to see a transit if the planet were transiting. The semi-amplitude, meanwhile, K, is analogous to the amplitude of the wave. It's the distance from the center of the wave to the peak, like this. The important thing with a semi-amplitude is you can actually use a semi-amplitude to get the mass of the planet using this equation right here. Alternatively, if you want to break it up into more common units of Earth and solar masses, and meters per second of the signal, you can have it rewritten as this. I got kind of cut off there. The important thing that you want to worry about when dealing with this mass, though, you would calculate here, is that the mass of this planet is actually what's called the minimum mass, or m sin I. So think about it like this. If a planet has a very steeply inclined orbit, as in it's not transiting, it's not edge-on, it's like closer to face-on, then the star won't just wobble straight forwards and away from us from our point of view. It's going to wobble radially, but it's also going to wobble tangentially. So forwards and backwards, but also up and down. And so that means we're underestimating the size of that wobble, and so we'd be underestimating the mass of the planet. It's really hard to figure out what the inclination of a planet is, or how inclined the orbit is. If a planet is transiting, then we know the inclination is very close to edge-on, and so the minimum mass is very close to the actual mass. But if we don't know it's transiting, it's really hard to figure out the inclination. And so in a lot of papers that tell us about the radial velocity of a planet, or get the mass of a planet from radial velocity, if it's not transiting, they'll just tell you the minimum mass of the planet instead of the actual mass. Which sucks, but it's really hard to get a more accurate estimate than that, so we can only kind of do what we have. The other 2 parameters, the eccentricity and the argument of periapse, are a little trickier to recognize. The eccentricity essentially describes how far away from circular the planet's orbit is, and a high eccentricity has the effect of making the planet's orbit less sinusoidal and more spiky. So you can see what this looks like for a whole bunch of different eccentricities and a whole bunch of different argument of periapse. You can see what a sample radial velocity curve might look like. For a perfectly circular orbit, this looks sinusoidal. But for a really eccentric orbit, the RV curve looks really, really spiky. The argument of periapse, meanwhile, rotates the orbit in space, so it kind of determines where along the orbit those spikes occur. And it's really hard to describe what an eccentric orbit looks like, aside from being spiky, for good reason. It turns out that for orbits with non-zero eccentricities, you can't actually model the radial velocity curve with a simple equation. Code actually has to model the orbit at each time to figure out what the radial velocity is. Luckily for us, though, most planets have pretty low eccentricities. This isn't a huge issue in practice, but you can still see what different radial velocity curves look like for different eccentricities and see how they change. And of course, this is normally just one signal out of many. So if you have multiple radial velocity signals, say you had 2 different planets in the system, you could add those 2 signals together just to get the final radial velocity curve. So you can see here a tighter, smaller period sinusoidal signal, probably from a planet, and then a much longer period one, probably corresponding to another planet. The reason I say probably is because it turns out that this is really tough to do in practice. Like we looked at this equation here, it's easier to, or just by looking at the power relationships that the mass of the planet and of the signal have with, say, the mass of the star, or the mass of the planet, or the period, we can get an idea of for what planets radial velocities work well. Radial velocities, this method, works really well for big planets and for small stars and for really short planetary periods. Now, of course, the same thing is true with transits. It works really well with big planets and small stars and short planetary and short periods. But ultimately, it's really tough to get around that. The very first planets that we ever discovered, main sequence planets, were discovered with this method. But those sorts of planets that we were discovering really early on were a type of planet called hot Jupiters. Really hot planets, really big planets that were really close to their star. And those are ideal for radial velocity methods. But it's really hard to find smaller planets, like say an Earth. So when looking at this plot right here, we can get an idea of what the typical uncertainty on a radial velocity measurement looks like. We can see we're getting radial velocity measurements that fit this model pretty well, but the uncertainties are on the order of a meter per second. On the order of a meter per second of movement of the star is about the best we can get. Now that sounds pretty good, and it is pretty good. But then you realize that if you go ahead and do this whole calculation, you kind of rearrange it to get the semi-amplitude on one side and calculate what the semi-amplitude of, say, the Earth is, the Earth's radial velocity signal is about 10 centimeters per second. So yeah, we're not really detecting Earths right now. Not unless they're really close to their star. So for a planet to have a large enough signal to be detectable, it needs to be big, close to its star, or have a small star. But maybe you could just say, oh yeah, we can just get more data, or we can just, stare our telescopes at these stars for longer to get more precise measurements. And we can, but we start to hit diminishing returns. And that's because of stellar activity. So I hate stellar activity. Stellar activity is what I spent my entire grad program fighting with. And it is the reason we have kind of not hit a limit, but we're hitting diminishing returns as far as getting more precise radial velocity measurements goes. So stellar activity just refers to the various processes going on in the star that can cause either spurious measurements or imprecise measurements. So there are a few different forms that they can take, but generally there are two different ways they can mess up your measurements. First off is stellar activity from what's called granulation. Granulation refers to all the paths of plasma that occur in the star and bring material up to the surface of the star and away from the surface of the star. But you might notice that if it's bringing stuff up to the surface of the star, that's towards you, and if it's bringing stuff away from the surface of the star, that's away from you. And so that will kind of mess up your measurements, because while the planet is trying to induce its own signal and cause everything that's emitting light in the star to move towards or away from you, everything in the star is kind of moving towards or away from you on its own. And so what this can do is it can induce variability on your measurements on the order of like 1 meter per second, which is about the uncertainty that we're hitting right now. The other type of variability is called star spots. Star spots are dim parts of the star that rotate around with the surface of the star. They can exist for days or weeks or sometimes months. But the important thing is that these stars, or these sunspots, can cause periodic signals in your radial velocity measurements that look an awful lot like planets. A star, depending on your star, it can orbit with a period of multiple days, or even dozens of days, which is the period that we'd expect to find these sorts of planets with the radial velocity method. And especially if you're working with small stars, the amplitude of these spurious signals can actually be larger than the planetary signals that you're dealing with. Small stars, by the way, are even more prone to sunspots than larger stars, meaning that working with small stars can get you a larger signal to find like low mass planets. You really need that stellar variability. The granulation is something that there are complicated methods to deal with, but right now we just kind of have that uncertainty in our measurements. But it can be a lot of work to measure out, to model out those sunspots and ensure that what you're looking at isn't a spurious signal. Luckily for you guys, when we get to the demo or the assignment, we're only looking at really, really massive planets that have huge signals that swamp both these out. But if you're dealing with lower mass stars, you need to be really worried about them. And ultimately, that's how we arrive here. Radial velocities aren't perfect. They only work for bigger stars, or bigger planets, as you can see. And they work well when you have, well, they work best when you have short periods, but they work better at longer periods than transits do. But like I said, radial velocities aren't perfect, but they are good for a lot of things. And a lot of times they're the only method we have for really detecting all those planets out in this region of parameter space. And so they suck at times, but that's the reason they're my favorite method of detecting exoplanets.
Register now on bit.ly/Intro2Astro 2024.